Hi everyone, welcome to this video where we're going to be doing a walkthrough of the 2024 AQA A-Level Physics Paper 2 paper. So let's get started. So in this question, first of all, we've got a room that contains dry air, temperature of 20 degrees Celsius and a pressure of 105 kilopascals. We're asked to work out the amount of air in each cubic meter, and we actually given the answer as a show question, and it says show that the answer is 40 moles. So bear in mind it tells us they're moles. Basically we're looking for number of moles, which is small case n, and is a show question, so we do know what the answer is. We have to give it to one extra significant figure. So I'm hoping it's obvious to most people we're going to need to use the ideal gas equation. So that's PV equals nRT, and then rearrange for n. Now, there's a couple of things that could catch people out here, which are the unit conversions. So this is kilopascals, so obviously times by 1,000, and we do need to put this into Kelvin. So we add 273, and that gives us 293 Kelvin before we put in our answer. So plug in our values in, so 105,000 times by our volume. Now it's just each cubic meter, which just means 1, and then divided by R, which is 8.31 from your data sheet, times by the temperature, which with Kelvin is 293, and we should get an answer of 43.1, which does round to 40 moles, given it's like that's the one significant figure. That's quite a nice easy start to the paper. This next one is a bit trickier. We're given some density of this air, which it gives us here, and we're asked to calculate the RMS speed for the air molecules. Now, there's a couple of equations that involve RMS speed. We need to look at which ones might be relevant. So let's look at data sheet for thermal physics. We've got a couple down here with RMS speed in. So we've got basically two, this one here, kinetic theory model, and kinetic energy of a gas. The one we're going to use is the one down below, the kinetic energy of a gas, because we do have temperature, and that's going to be really useful to work out our RMS speed. Now, there are a couple of ways of doing this. You can do it using the other equation if you want to. I'm going to do it using this one though, because I think it kind of makes a little bit more sense. So average kinetic energy, we can write the equation down here, equals 3kT. Now, to be able to use this equation, we're trying to find this thing here. We know what T is, we don't yet know what this is. Now, it's important to note this is the mass of one molecule. It's not the total mass of the whole gas, it's just the mass of one molecule. But we can't work that out. I'm going to show you how we can work it out. And K is just a constant. So to work out the mass of one molecule, what we can do is do the total mass, which we're going to find out in a second, divided by basically the number of particles. So once we find out those two things, we can then work that out. So total mass of the whole system is going to be equal to density times by volume, because density equals mass over volume. We know what the density is. We know the volume of each cubic meter up here is about 40 moles. So we can use that and just use V is 1 basically. So therefore we've got for the density times by the volume just equals 1.25, and that's kilograms because V is just 1. Next, once we do that, number of particles. So this can be a little bit tricky for some students, especially if you don't do A-level chemistry. So first of all, we need to find the number of particles is equal to the number of moles times by Avogadro's number. Avogadro's number is the number of particles in 1 mole. We need to know how many moles times by that. We luckily know from earlier in the question, because we are asked to show it as being 40 moles, or we can use the raw value 43.1 moles. So I'm going to do this. So 43.1 moles times by Avogadro's number, which is 6.02 times 10 to the power 23. So let's work out the number of particles. Okay, so plugging our numbers in here. So if we do the mass divided by whatever that equals to, we get the mass of one molecule, which is very, very small, but that makes total sense, is just a couple of extra sig figs, 4.81766 times 10 to the power minus 26 kg. Sorry, it looks a bit messy there, but let's just do it in the wrong order. Once we know that, then we have everything we need to use this basically. So let's rearrange this equation and to be able to find what the root mean squared speed is. So rearranging for this, we're going to put the half onto this side. So basically the two halves will cancel out effectively, and we're left with, so RMS squared equals, if we multiply this one here, so we're left with, let's do the whole thing, so I'm not going to have room otherwise, 3kT over the mass of one molecule. Okay, so mass of one molecule we know down here is equal to this. So if we put our numbers in, K is Boltzmann's constant, so which one's that, 38 times 10 to the minus 23, times by the temperature, which is 293, all over the mass, which we've just found, which is this thing here, so 4.8 I'm going to round that 4.82 times 10 to the minus 26. And if we do that whole thing as a square root, we should find it's 501.7-ish, which I'm going to round to 3 sig figs. It is important here you're rounding it to the correct number of significant figures. They remind you about it in the question. If you look back to earlier in the question, if you do a quick look at the number of significant figures we already have, we have this is 3 sig figs, this is 3 sig figs, this is 3 sig figs. This isn't, but your answer here is 3 sig figs. Weirdly in this question though, the mark scheme allows you to do it to 1 sig fig, because this could be 1 sig fig, as long as you're consistent with your workings basically. But I would definitely just go with the raw numbers here. Everyone else is 3 sig figs. So that makes a lot more sense in my opinion. Okay, next question. We've got calculating the change in Kelvin or temperature that will double C RMS for the air molecules. So let's have a look at what the relationship between those two things are. So just looking at these two relationships here, between these two things, we've got basically RMS, C RMS squared is directly proportional to temperature, because this is a constant and the mass of the molecule doesn't change either. So basically for this to double, what has to happen on this side to make this whole thing double? So I'm hoping you guys can spot this because it's squared. So 2 squared is obviously 4. Therefore, we're going to need an increase of times by 4 on this side for the temperature to make an increase of times 2 for the root mean squared speed. So we basically then need to look at our actual values, because it does say calculate, it's not just a relationship question. So T needs to be 4 times what it was originally, so 293. So 4 times 293 equals 1172. Then we need to do that. So that's the total final temperature that would cause this change. So then work out the change in temperature, the very specific change in temperature here. So we do 1172 minus the original, which is 293. And if you do all that in your calculator, you should get 709? No. If you do all that in your calculator, you should get 879 Kelvin. Moving on to the next question. This one is one of the tricky ones in the paper, I would say, and it takes a lot to wrap your head around what's going on. Please make sure you understand it. Like, don't just look at the mark scheme. Like, the mark scheme is actually not long for this, but to actually understand what's going on, it's weird. And this table is weird. It's just one of those ones where you would never have seen a question like this before. Basically, you've got a room which contains moist air, and there's going to be essentially a dehumidifier that's condensing the water, and it gets cooled as well. So you can see the different temperatures here. We actually don't need those for this question. We do know, however, in 1 hour, there's a volume of 960 meters cubed that flows through it, and the density is the same as earlier, 1.25. We're asked to determine how much heat energy is removed in 1 hour from the water by the dehumidifier. And we're given, here's the big clues here, you're given the specific heat capacity and the specific latent heat. So effectively, we are just looking at the water. So how much energy is going to be sort of released as it's going to be condensing, then as it's cooling as well. So basically, we are just looking at the energy of the water. So I'll do the final calculation at the end, but effectively we're going to be looking at the total energy that we are talking about is going to be the energy that's used to cool the water, so MC times by the change in temperature, plus the latent heat effectively that's being used to change it from a gas to a liquid. So I'm going to write those down here. So gas to liquid, and this bit here is just for it to cool overall. However, in both of these, obviously you need the mass of the liquid that happens to. We don't have the mass, we have the mass of the water divided by the mass of the air. So let me show you how to sort of work out this kind of question. So it is basically, even though it's two things that are divided by each other, which is a bit tricky, it is just basically an equation. So this is mass of the water divided by mass of the air. Now, if we look at those, the change between what comes in and what comes out, so the change in that fraction there, that ratio, mass of water divided by the mass of the air, we can find by just subtracting those two things. So if you do 0.0057, take away 0.0037, we're left with 0.002, which makes life a bit easier to deal with. And the important bit is, now we know what that is, we're trying to find what this mass of the water is, so we can use it in our equation. We need to know what the mass of the air is, but luckily they've actually given us enough information to solve that. So for the mass of the air, we know that the volume of air is 960, we know the density is 1.25. So therefore the mass of air, we just do the density times by the volume. So that's going to be 1.25 times by 960, which is going to be, put in that calculator, so that's 1,200, and that's kilograms. So then next, what we do is we then use this equation up here and we say, all right, so for the mass of our water, or just the change in mass of water, basically. I should put the delta in there, shouldn't I? We're going to essentially have, so the ratio of those two divided equals 0.002. So if we times that by the mass of the air, we are going to be left with our mass of water. So that times by 1,200, and that equals 2.4 kilograms. Okay, so that's our mass of water. Now we know that, we can just come back to this equation here and essentially just sort of plug in our numbers. And as long as we keep an eye on the correct temperatures and things like that, we should be okay. So temperature is equal to 2.4 times by specific heat capacity 1860 times by the change in temperature. So the change in temperature for this question is just 10 degrees because it goes in at 20 and it says it collects at 10 degrees. So the change is 10 overall. And then add that to, I should probably factorize out the m, shouldn't I? But too late now. Times by the latent heat, so 2.3 times 10 to the power 6. And if you put all those together, you should get the heat energy removed to 5.6 times 10 to the power 6, which is quite a lot of energy, but I don't know, it doesn't sound too crazy for what we're doing here. And that's your final answer. So quite a tricky question to understand what's going on. Once you've realized this bit, the rest is just putting numbers into that equation. Next up, question 2, we've got a question all about capacitors. So quite standard capacitor circuit here. We've got a charging capacitor and we have the known capacitance of C, and we are having the switch closed, and then basically the potential difference is recorded at different time intervals, very similar to the required practical for the AQA syllabus. This question is asked to explain how a gradient of the graph here can be used to determine the initial current in the circuit. So this one's a little bit trickier than you might think. There's 2 marks in this question, and quite often if you were to have this question, you could be asked to find the current and it'll be a charge time graph. It's not, it's a voltage time graph, which makes things a bit trickier. However, if we know our definitions and we use our equation sheet well, this is not too bad, I don't think. So current overall is equal to a rate of flow of charge, or delta Q over delta T. However, because it asks us about the gradient, we do have to refer to the gradient. The gradient for this graph is equal to the voltage, or change in voltage, divided by change in time. So effectively, we've got to figure out how do we go from voltage to charge. Now, there's an equation in your equation sheet, which is very essential for the capacitor topic, which is that Q equals VC, or C equals Q over V. So to be able to use that and to be able to link these two together, effectively, we can rewrite this. We can say, instead of change in Q, we can say that's equal to change in V times by C over change in time. Note the capacitance is constant, so that's not changing, so it's only be correct to do this bit here. Now, we said earlier, change in V over change in T is going to be equal to the gradient, so therefore we could just rewrite this and say the gradient, which is V over T, times by the capacitance, which is constant, okay? Now, final thing is that actually, I missed out one little bit here, which is to say it's the initial current, so the initial current in the circuit. So therefore, we would have to, if you were doing this question properly, you'd get a tangent for this bit here, and you'd work out tangent of this bit, this little part here. So because it says initial current, it's going to be the initial gradient times by the capacitance. So that bit there rather than the gradient at any point, because obviously the gradient is changing. So as the potential difference across C is charging, potential difference across R is effectively a discharging circuit because it's decreasing in R, it's building up over C. Then we've got a discharge voltage time graph over here, which we're asked to find the time constant and then find R, and it is a show question. So we do know kind of what our final answer should be. So for this question, time constant, we need to know, so for the time constant, that means the voltage has dropped to 37%, or e to the minus 1 of its original value. So 30% of V naught. So to work a time constant, we should use the graph to do that. So this starts on 0.62. So in your calculator, find 37% of 0.62. Which obviously we talk roughly here, but that's 0.2294, let's say 0.23, I think that's close enough. So get a ruler out, and then we go, each square is 0.02, so I go halfway between this square and this square, do it properly, do it with a ruler, and then go down, and we should find that that is 27.5. However, that is not the time constant, because a little bit sneaky thing they've done here is they haven't done a false origin, but they've just started on 20. So the time taken for it to go from there to there is 20 to 27.5. So the time constant is going to be equal to 7.5 seconds. Once we know that, and we just write that down here, we don't need any more calculations, I don't think, is to know that time constant is going to be equal to RC, which we know what the capacitance is because earlier in the circuit, in the question, so 7.5 equals R times by our capacitance. Yeah, it's earlier here, so 31 microfarads. So then we get our capacitance is 7.5 divided by that, which is 250,000, which kind of is close enough basically. I mistyped my calculator, I put 30 instead of 31. So there you go, this a bit more, I was getting a bit worried there. Okay, so 2.4, this rounds to 2.4, 2 for me. So just keep the 2 sig figs is fine anyway, but yeah, that definitely rounds to 2.4 for this question. On to our next bit of the question. We know the current I0 at time at the start of the experiment is 3.6 times 10 to the minus 5. We are asked to determine the time at which VC is 6 volts. So let's go back to our graph on the previous page. So we're looking at VC here. It's really tempting to just use the discharging capacitor equation here for this graph. However, this is VR. That's the potential difference across the resistor. We are actually charging the capacitor up. So when we're looking at VC, it is the charging capacitor equation. So make sure you're using the right equation here. It's very tempting just to do the discharging one and not think about it. Plus it's on a separate page, which is always a bit mean, I think. But the calculation for charging capacitor in your equation sheet is the one that's kind of got the 1 minus in it. So V equals V naught, and then 1 minus e to the power t over RC. That's the correct equation to use. So what we don't have yet, we do have the time constant. We're trying to find the time. We don't have V naught. However, it's not that bad to work it out. So we know the current I naught is this. We do have from earlier in the question the resistance because we're asked to show it. Don't forget, often if they ask you to show something in a question, you do have to use it for the follow-up question or a question later on. So V naught equals the initial current times by R. So that's 3.6 times 10 to the minus 5. And the resistance was 2.4 times 10 to the 5, which means we're going to have our initial voltage is going to be times those together 8.64 volts. So now we have this. So other than that, it's just a way. It's just how we manipulate this equation, which it is harder than the discharging one because I know you've got the 1 minus in it, and I think it's just a bit trickier. So how we do it basically is to do the ratio one first of all. So V over V naught equals, and on this side we now have 1 minus E times that. We need to get the 1 over to this side as well, so we can take natural logs. So I always do, so switch the over here, switch the V over V naught over here. So we'd end up with 1 minus V over V naught equals E to the power minus T over RC. Once we know that, we're taking natural logs of both sides, and I'm going to start plugging in my numbers. So 1 minus the V, which we are looking at now, so VC is 6 volts, so 6 over the initial 8.64 we worked out earlier equals, and then minus T, which we don't know, divided by the time constant. So you could do RC, but we did work out the time constant earlier, which is 7.5. So let's just save a bit of time and do that as well. So then we should find basically if we work this side out and times by 7.5, we can then work out our time taken to get to 6 volts. So if we do all that, we should find that we get, obviously the 2 negatives will cancel basically on this side and this side, and that should come to about 8.9 seconds, which seems reasonable. Usually for a practical, you're not going to have milliseconds or anything for a sort of lab practical. So yeah, quite a tricky question, that one. Definitely get the first mark, that shouldn't be too bad, but then how to use this equation, how to spot that it's that one, that one's the right one to do. But that's how you get the answer for that question. Next up, we got a quite scary looking question where we've got 2 capacitors in parallel, which for AQA it doesn't mention you need to know about in the specification, but we don't necessarily need to know loads about what the capacitors are doing. It's just there's 2 different capacitors and they have 2 different voltages across them, and all the information we need is in the table. Okay, so there's comparison of lots of different properties of these capacitors. I'm just going to cross out the ones we don't need to worry about. So charge is the same, surface area is the same. We're trying to look for potential difference of V1 over V2, and then we basically are focusing on these ones here because this is where the differences are. So V1 and V2, we first need to work out how does like the dielectric constant relate to voltage. So there's only one equation with dielectric and plate separation in it, which is this one here. So capacitance equals permittivity of free space times by relative permittivity times by cross-sectional area, got D in the wrong spot there, divide by D. Now, because the area is the same, we can basically ignore that, and permittivity of free space is constant, so we can ignore that. It's these two things that are changing. So effectively, we've then got capacitance is proportional to the relative permittivity divided by D. However, we're not asked about capacitance, we're asked about voltage or potential difference. So I mentioned this equation earlier, but a quite fundamental equation for capacitance that links the two together is Q equals VC, which if we rearrange for V, obviously we have Q over C. Now, what's really important here is because it does clearly say the charge is the same for both. So effectively, this boils down to the fact that voltage and capacitance are inversely proportional to each other. So that's going to really help us, because if we then do voltage is proportional to 1 over C, instead of C, we can then write in this thing here, so ER over D. And that's our general sort of expression. Obviously, simplify it down, so V is proportional to, obviously that comes to the top, so that one comes to the top, D over ER. So if those two things are proportional, then we can do, I'm going to take up loads of room here, which is probably unnecessary, but hey-ho. V1 over V2, therefore, is going to be equal to the ratio between, so D1 over D2, and because it's inversely proportional to ER, it's going to be times by ER2 over ER1, because they're inversely proportional. Once we've done that and just looked at the ratios, it's just a matter of plugging numbers in, basically. So D1 over D2, D1 is going to be equal to 4, then D2 is going to be equal to, can't speak, D1 is 1, and that's half, so basically this is a half. And then I was looking at dielectric constant. Dielectric constant is going to be, so 1 over 4. So on this side, we're going to have 4 and 1. And that equals basically a 16th. That equals an 8th. I'm missing this question up, aren't I? Which you can write an 8th if you want, but 0.125 is how the mark scheme phrases it. Quite a tricky question, that one, in my opinion. First question here about magnetic fields, and I've never quite seen a question like this when we're asked to use the Earth's magnetic field, and we've also got a bit of sort of projectile motion, a bit of paper one mixed in here as well. So let's have a look at what we've got. This one is quite tricky, along with 3.2 in my opinion. So there's a conducting rod, which you kind of can't really see, but it's going into the page. It says the magnetic flux density of the Earth will be given is 4.9 times 10 to the minus 5, and the angle is 68 degrees to the horizontal. And the rod has a length of 2.0 meters, which we can't label, but that's the length of it, sort of going in the page east to west, because we've got labeled north and south this way. It gets released and it falls 8 meters to the ground, stays horizontal. We're asked to determine the average EMF across the rod during its fall to the ground. So tricky question, but one of the clues we're given is the magnetic flux density B. So if we're trying to find average EMF, there's a real big clue there, is to say Faraday's law is EMF is going to be equal to rate of change of flux or flux linkage, but we don't need to worry about flux linkage, only one rod. So therefore it's change in flux divided by time. So we need to work out basically those two things separately, and that'll give us overall our average EMF. So how do we do that then? Let's rewrite this a little bit. So flux is equal to flux density times by area. And then what we've got to do is figure out how to get this angle involved here. So what do we have to do how do we basically modify this equation to get that 68 degrees involved? So we get to modify this equation to be BA times by cos theta. So two ways of looking at it. It does basically have this version of it in your data sheet when you look at flux linkage. Second thing is to look at, well, we're looking at the motion of the rod. We are only concerned with the motion that is perpendicular to the field lines, because that's when EMF would be induced. Hypothetically, if the rod was dropped like that in the same direction as the field lines, there'd be no EMF. So we're just looking at the component of it that's perpendicular to the field lines, which in this case is cos theta in that direction. So let's work this out then. So B is 4.9 times 10 to minus 5. A is an interesting one. Now, I know you can't see it, which I think this question is really mean. But if you were to imagine this rod itself, you can work out basically the area it sweeps through by knowing it goes down by 8 meters. And the rod itself is 2 meters across. So the whole thing, as it goes down, it's going to sweep out an area of 8 times by 2 meters. That's the sort of area of the magnetic field it gets through. So the area would just be 8 times by 2 basically, and then cos 68. So if we work all that out, that should give us our magnetic flux, which is, I haven't labeled this properly, have I? There you go, sorry. That's equal to that. And that's 2.94 times 10 to the minus 4 Webers, which is quite small. It's usually quite small. Now the time taken we don't know, okay, but we can use a bit of SUVAT to help work it out. So to work out the time taken, if we know basically it's fallen to the ground, it's under the influence of gravity, we could use one of our SUVAT equations. So S equals ut plus half at squared. There's no initial velocity because it's dropped. So therefore, if we rearrange this equation, t equals 2s over a, all square rooted, which is equal to 2 times by 8 over minus 9.81, should be minus 8, sorry, and then all square rooted, which gives us a time taken of 1.28. So therefore, final step is just to combine those together. So we've got magnetic flux, or the change in magnetic flux, and we've got the change in time when it's happening. So we just divide the EMF is equal to 2.94 times 10 to the minus 4 divided by 1.28, which should be equal to 2.3 times 10 to the power minus 4 volts. Alternative ways of doing this, there are a couple. You could do, so this isn't in your equation sheet, but it's kind of, you could derive it from Faraday's law, is EMF is equal to flux density times by the length of the rod times by the velocity, and then use a bit of sort of, I think, SUVAT you probably use to work out V. And personally, I think this is the easier way of doing it, so that's the way I've done. Next up, there's a bit of a change to the setup, and it's a good test of sort of how well you understand magnetic fields, this question, I think. So the rod is returned to its original position, but now it's supported by a non-conducting pole that's hinged on the ground. It says the pole is initially vertical, then it's released. It can either go left or it can go to the right. And it's asked you to say there are changes in the magnitude and direction of the induced EMF depending whether it falls each way. Explain these changes effectively. So just to get clarity on the setup, so basically here's the rod as before, but there's a pole, and essentially the rod can either fall that way or it can fall this way. So it's on a hinge, so it falls like that or like that basically. So let's talk about the left first of all. So we kind of touched on this earlier when we talked about the field lines bit. So essentially as it falls to the left, basically the angle that the rod is going to make with the horizontal is going to decrease, okay? So effectively it will get to, there'll be a point at which it's parallel to the field lines because of the way it's sort of falling. So it will fall at some point, it will fall like almost like probably about here, exactly in the direction the field lines are going, which means there'll be zero EMF there. So let's just write this out. So when it goes to the left, basically the angle is decreasing. So this angle here, but it's the only angle in here, so we just say the angle is decreasing. And then basically it will decrease and then it will start increasing again before it hits the ground, essentially. So therefore we could say the angle decreasing, then decreases to 0, I'm going to say, then increases again before it hits the ground. So changes in magnitude and direction of the EMF, basically what happens is that you're going to have basically a small EMF induced, which is 0 when the motion is parallel to field lines. Now, there's loads of marks you can get for this question. Well, I say loads, but quite a few different marks you get for this question. But basically, each one they want a statement of what happens, and then you want like a reason why, basically. So essentially, for this bit of the question I've done is the mark for the fact that it goes small EMF induced, then 0. It's because the motion is parallel to the field lines, effectively. So there's lots of other things you click on the mark scheme. I'm not going to write them all out here because I haven't got much room, but that'll be an example for a statement when it goes to the left. Next, let's talk about the right. So it's kind of the opposite if you think about it. So this time, let's just talk about, instead of the magnitude, let's talk about the direction of it, just to sort of talk about which one happens. So if it goes to the right, it's cutting across lots more field lines, and about here is exactly perpendicular to the field lines. So you're going to have a maximum EMF before it goes back down here. So essentially, you could say the direction for this one stays the same. So I know it's not a direct comparison, but I'm talking about direction because they gave us an option of talking about that as well. So the direction stays the same, so the EMF direction stays the same, I should say. And that's because the rod is cutting across the field in the same direction. So check out the mark scheme. It's linked in the description if you want to have a look at more different options you could say. But there's been an example of things you could say with the point and the explanation for 4 marks here. Quite a tricky question, but it's a really useful one to make sure you understand what's actually going on with EMF and how it relates to the direction of an object relating to the Earth's magnetic field or magnetic field line. Okay, for question 4, we are talking about nuclear reactors. So we're talking about coolant. So one purpose of the coolant in a thermal nuclear reactor is to maintain a safe working temperature within the core. What is another purpose? So the purpose inside the reactor is basically a coolant is basically supposed to extract the heat. So we just say something like it extracts the heat from the core, because otherwise the heat just builds up and the thing will blow up. So it extracts the heat from the core and then takes it to the boiler or the furnace, not furnace, the boiler or something like that. And you could say via the heat exchanger. You don't need to have that bit for the mark scheme, but I think it's a good extra bit of information to write down. Next one is state 2 properties that engineers consider when choosing a liquid to use as a coolant. So this isn't massively about the nuclear reactor, it's just about the liquid itself. So what might be good properties we want to use? We want it to have like a relatively, so to be able to extract the heat, we want sort of, you talk about the specific heat capacity, so that might be the right thing to do. So that means you need to give it a lot of energy before its temperature raises too high. Otherwise it's going to sort of end up boiling, which is obviously a problem. We could say you want to have ability to flow, so high viscosity. And there are some ones specific to a nuclear reactor here. You could talk about so high boiling point as well, you'd want there. So one specific to a nuclear reactor might be you don't want it to absorb neutrons, because if it does that, that will then act as a control rod, which you don't want it to do. You don't want to slow down the reaction. So its ability to absorb neutrons is important as well. So I mean, I've given 4 there, but those are things you write down for your 2 marks. Next one, it says, how is the power output of a thermonuclear reactor decreased? A little bit easier, this one, I would say. So what we do is we insert or lower control rods into the reactor. And the reason we do that, control rods into the reactor, is basically to reduce, so control rods absorb neutrons. You want to reduce the rate of fission reactions, basically. And you could say about absorbing neutrons, but you actually need that for this mark, which is interesting, by absorbing neutrons. That'll be absolutely fine for your 2 marks there. Next up, we've got gravitational fields. So an interesting situation here where we've got a satellite, which is S1, and that's placed sort of the other side of the moon, so that you've got between the satellite and the Earth, you've got the moon interacting with it as well. It tells us it's got the same angular speed as the moon. That'll be important later for 5.3. And let's have a look at what we're asked to work out first of all. So the resultant force on S is due to the gravitational forces from the Earth and the moon. So effectively, as you might expect, it's going to experience a force. I can't reach all these on properly, it's not much room, but F due to the Earth and F due to the moon. This is a bad idea. That looks horrible. Anyway, 2 forces go in that direction. The magnitude of the Earth's gravitational field strength is this. So it's not 9.8 because it's not on the surface of the Earth, obviously. And we are given that was asked to show that GM, so the gravitational field strength of the moon, is that. And we are given the period of the moon's orbit and the orbital radius. So let's have a look at how to do this. This is tricky. It took me a little while to sort of figure out exactly how to do this one when I looked at it. So the general idea is for gravitational field strength, the overall gravitational field strength, so the total, is going to be equal to both of these added together. So gravitational field strength of the moon plus that of the Earth. So in the question, we are given the gravitational field strength of the Earth, which is 1.98 times 10 to the minus 3. And we know, we're given this one here, and we've basically got to work out, to be able to work out the gravitational field strength of the moon, which is what we're asked to in the question, we've got to work this bit out here. So the overall gravitational field strength is a really important thing we need to realize, is that overall gravitational field strength is basically equal to centripetal acceleration of the object as it travels around. So let me show you how that sort of works. So we know G is equal to F over m, so the force experienced per unit mass. which is Newton's law of gravitation, gm m over r squared, and then obviously divide by m, so we cancel one of the masses. So g is big G m over r squared. Now, because it's going around in this centripetal motion, we can basically say that's equal to, so the force per unit mass is equal to the centripetal acceleration. So I'm going to say m omega squared r, omega because we've got time period here, that's going to be useful. And again, we've cancelled one of the m's because we're doing force per unit mass. So you could do that in terms of force, then just divide through by m. Doesn't matter, that long way around there. But the whole point is that g, gravitational field strength, is equal to omega squared r, which is the same thing as centripetal acceleration. It's literally the same thing. So let's work it out then. We know what omega is. We can work out what omega is. So this is going to be equal to 2 pi over t, which obviously has to be in seconds. So 27.3 times 24 times 60 all squared. Put an extra bracket in there. Times by the radius of orbit. So 4.489 times 10 to the 5. 10 to the 8 because we've got to do in meters. Yep. So if we do all that, we should get basically 3.19 times 10 to the minus, we'll do minus 3. So that's basically the overall gravitational field strength that's acting on it, because it's the centripetal acceleration, because it's providing the acceleration to keep it in a circle. So that's equal to the total G. Can't spell total, there we go. So once we know that, G of the moon is equal to essentially this minus this, so the total minus that from the Earth, which is the thing we just calculated, 3.19 times 10 to the minus 3, minus the value given to us, so this is gravitational field strength of the Earth, 1.98 times 10 to the minus 3, and that all equals 1.21 times 10 to the minus 3, was it newtons per kilogram, which thankfully is what we're asked to show, so an extra significant figure than what we're given in the question for our 3 marks. Now that's quite a tricky one. Next up, this isn't too bad, and quite often questions work like that. A really horrible one, and next up, this 2 marks is really quite nice. So don't be put off if you just spent ages on a question you can't do it. Just make sure you can do this one afterwards. So I overwrote this equation down earlier. Gravitational field strength equals G capital M over R squared. So we're trying to find the distance from S1 to the center of the moon. So let's rearrange the equation for this. So we have R equals GM over capital GM over gravitational field strength of the moon. And then just plugging numbers in. So universal gravitational field constant times by the mass of the moon, which we have given here, and then divided by GM, which again is a show question. They're almost always going to get you to use that in the question afterwards. And if you do all that, we should get the distance to be 6.37 times 10 to the 7, which kind of makes sense. That sounds reasonable for an astronomical distance. Final question in this gravitational fields question. It's kind of tricky. There's no calculations. And they basically change where the satellite is. All right, so let me talk through it. So we got another satellite. It's placed in a circular orbit between the Earth and the moon, so not this side this time. It's always on this side of the moon, and it tells you they have the same angular speed. So when they orbit around, they're going to orbit exactly the same angular speed, so the same time period. So center of the Earth all in a straight line. Shows the 2 positions, blah, blah, blah. Explain how resultant force on S2, due to the gravitational fields of the Earth and the moon, causes them to orbit with the same angular speed as the moon. So basically explain this using the idea of resultant forces. So first of all, resultant forces, the first mark is really not too bad at all. We've got a resultant force going this way, which is due to the Earth, so Fe, and we've got a little force here, which is obviously going to be lower because the moon's got a lower mass from the moon. So we essentially say that the force due to the moon is in the opposite direction than the Earth, because earlier on the question that was not the case. They're both in the same direction. Next we've got to talk about is like why they all give the same angular speed, like what's going on there to cause that to happen with the same angular speed. So if you consider the fact that there's a difference in radius between these two, so basically if you've got a orbital period that's actually going to be quicker the closer you are to the Earth, as opposed to the moon, which is going to be slightly longer orbital period because it's a bit further away. So basically, how do we phrase this? Let's say something like, so S2 has a smaller radius of orbit. So we'll have, and basically without the moon overall, it would have a smaller period of orbit. So let's say, for example, if you've got something really close to the Earth's surface, like the ISS, that has an orbit of like 90 minutes or something like that, I think. So really, really low T, because it's so close, it's traveling a lot, has a lot higher linear velocity basically as it goes around. So that's basically without the moon. That's how the moon's effect. Then we talk about, well, what is it about having the moon on this side that actually makes a difference? So with the moon essentially reduces the resultant force, or basically the centripetal force for S2 because of its gravitational force or gravitational field, which essentially reduces the angular speed. And if we know angular speed is 2 pi over t, then if you increase the angular speed, we're going to be decreasing if we're going to be increasing the angular speed, we're going to be decreasing the time period, basically, which will allow them to orbit at the same speed. Bit of a weird odd question, that one. That kind of doesn't make sense, but the mark scheme is kind of quite annoyingly specific. But that's how you'd answer that 3-mark question to finish off the gravitational fields question. Next up, we've got electric fields. So we've got a electric field, which it tells us the potential at that point is -4 volts. Explain what's meant by this statement. So really, really vague. However, it's really not that bad. Basically, it could be the same kind of question as like, what is electric potential? Define electric potential, because that's essentially what the question is. So for this question, basically what we'd say is that it's the, basically there's -4 joules of work done in moving a unit charge, or a positive, we should positive, shouldn't be a positive 1 coulomb charge from infinity to a point. So how you build that answer up is you'd say, well, I know potential is work done per unit charge, and it's got to be per unit positive charge, so that's marked there. However, because it's negative, it's got to be negative work, and because it's -4, it's got to be -4 joules of work. And the definition of potential always we define it as going from infinity to a point, basically. That applies to all of them. So the only thing that's a bit unusual is this bit here, but potential being work done per unit charge from infinity to a point, that kind of definition comes up all the time. It's just they've given you 3 separate bits for this question. My students, along with lots of people, hated this question when it came out in 2024, partly because it's just a bit weird. There's a bit of a weird setup, but I'll talk you through it. Some of it's not as bad as it might seem at first glance. So we've got an arrangement for confined groups of electrons to small regions in this block of this thing called gallium arsenide, where you've got these 2 confined electrons here. And the tricky bit about this question is this whole bit here corresponds to a graph. It says electrons can only move along the line PQ. So basically this way, when you apply a suitable potential to the electrodes, the electrons are confined to those regions. And basically, the only thing we need for 6.2 is the idea that the graph shows how electric potential varies with distance along PQ. And while it's a difficult question, and yeah, this question, the one after, can be really tricky, this one is really not that bad, because it's the kind of question you could have just without the context anywhere. So it says use the graph to find the maximum magnitude of the electric field. So the maximum magnitude of the electric field, what we're going to do is use the equation from your equation sheet. Electric field strength is going to be equal to change in potential divided by R, which is also known as the potential gradient. And basically, because this graph here, you've got potential on the y-axis, you've got essentially R, I know it's X, but on the x-axis, essentially we're going to try and find the maximum gradient. So we've got to find the max gradient that will give us the maximum value for the EMF. So let's have a look at where that might be. So gradient is obviously, we can use a tangent because it's a curve. So it's not going to be anywhere where it's flat or anywhere where it's going downwards like that. It's going to be either here or here overall. So just line your ruler such so basically it's as steep as it can be while still working out a tangent. So I'd go with about there, I'd say. forgive me if it's wrong. I'm not going to do it in pencil because it shows up better if you do it in pen. So once you've drawn that line on, we're effectively going to draw in a triangle and then basically work out what the value the tangent or the gradient of that tangent is overall. So let me draw that on there. Let's work out. So I've done it so that the change in y is relatively straightforward. It goes from 0 to 3.75 minus 3.75. And then for my x-axis, I've got God, I thought I did this simply, maybe not. That's 2 squares down from 100, so 3 squares down from 100, so that's, I've got that 70 nanometers, and it goes to 3 squares down from this one. Okay, so that's quite nice. That's 270. So let's then just plug my values in to work out my gradient. So change in potential was 0 to 375, so minus, it's not minus, sorry, it's just regular 3.75 divided by, and the difference between, so 270 minus 70, and be careful, this is in nanometers, so times 10 to the power minus 9. And let's see how close this is to the mark scheme. Okay, so that's got 1.875 times 10 to the power 7, which is just within the range, not too bad. The range is 1.8 to 2.2, so we'll stick with that. So round out 1.88 times 10 to the power 7. And there's 2 alternative units for electric field strength. One of them is volts per meter, which I think is the easy one to remember because it's kind of from the equation. The other one is newtons per coulomb. Either of those would be absolutely fine. Okay, here's where the real fun begins. So we've got an electron in the next question at rest at x is 300. So basically here, gains kinetic energy and moves to x is 800. So what's that over here? Determine the minimum kinetic energy required by the electron. So even though it seems horrible, you don't need to understand really the theory behind it to be able to do this question. But basically, it can be confined here because it's got a minimum potential and minimum electric field strength because it's a flat line there. And then you go over here and it'll be the same region there. For it to gain kinetic energy required by the electron, it's going to be equal to basically the gain in potential energy or electric potential energy. So the KE gained is equal to, or again, required to make that leap is equal to potential energy, electric potential energy, essentially. So that equals work done per, I'll explain as well. Work done is equal to then QV. So electric potential energy is just charge times by potential difference. So in this case, that's going to be equal to the charge on the electron, so 1.6 times 10 to the minus 19, times by change in potential. So the change in potential when it goes from here to here, we need to be a little bit careful about how we're measuring this. So for our change in potential, it goes from here where V is, we can read it off the graph. So that's 0.2 minus 0.2. And it goes up to the peak up here, which again, let's read off our graph. They're all the same, so we can choose any one, but that's minus 3.4. So therefore the change in potential difference, you could include a little delta V in here, but it's the same thing. It's going to be equal to minus, so 3.4 minus 0.2, which is going to be equal to, obviously that's 3.2 overall. So times those two things together, and we should get 5.12 times 10 to the power minus 19, which sounds kind of reasonable. It's just one electron, it's a very small number, and that's the amount of energy it would need to make that leap. Okay, next question, and the last one for this question 6 is, in my opinion, the most tricky one to sort of get your head around. It says there's one of the confined electrons is at x equals 350, so that is 350 is about here, so we're talking about there. Discuss the subsequent motion of this electron due to the variation in electric potential as shown in figure 9. So basically everything else is the same, but let's say it's an electron here, what is it going to do? So there's a couple of things to note, first of all, which is that all this potential here is negative, okay? So when we talked earlier about getting sort of higher potential or lower potential, that's all of it is negative. So the fact that it's an electron and also negative makes a big difference here. Okay, so essentially overall, we need to talk about, first of all, which direction it's going to go in. So like initially, and then what will happen to it a bit afterwards. So generally speaking, so the electric field strength is going to be obviously higher to the right. So from where it is now, so the particles are here, is going to sort of try and put it towards this direction. So if it was a proton, for example, it would move this way because you've got a more negative field strength down here. However, because it's an electron, that's going to actually sort of repel and push it back this way. So it's going to go back in this direction. So we'd say something like the electric field strength direction is to the right, but because our electron is negative, it moves to the left. And that's enough to say moved, first of all, and we'll talk about the other bits in a sec, but it moves initially, I'm going to say towards this point here, so x equals 300 nanometers. So now that we've got that out of the way, and that's a couple of marks already. I know I've not done it nicely in bullet points, but that's a couple of marks already for what happens. So the reason, if you didn't catch it, the reason it's electric field strength directions to the right is because the gradient is steeper on the right-hand side of it, as we did with the earlier question. So this bit here, so that's higher to the right of the particle. So because it's an electron though, it's negative, so therefore it's going to go the other way. So it's still the opposite of the way the proton would go, basically. So next then, let's talk about, and you could mention that gradient in here, I think that gets you an extra mark, but I'm not going to do so. What's going to happen then is essentially, it's going to go back to this part here. So it's going to lose eventually, so once it gets past that point there, so x equals 300 nanometers, it will lose kinetic energy, and it will gain potential energy. So it will won't just stop miraculously, it'll go past this point and it'll go up this way a little bit. So it'll go, I know, to x equals 260 or something like that. Then it will go back down because this time the field strength will be pointing to the right, the left direction. So it's an electron, it will go back right. So this way, and essentially it will oscillate. So it will oscillate sort of back and forth about the x equals 300 nanometers point. Kind of like a pendulum, basically. So similar thing, even though it's gravitational potential in a pendulum as opposed to electric potential, it's all the same thing. It'll eventually rest around the equilibrium point, but that's sort of what it'll do initially. So very weird question, that one. Have a look at the mark scheme if you want to look at all the different points you could get. I've written down 4 there. I've only 3 marks available, but yeah, quite a tricky one that to finish off the question on electric fields. Okay, lastly, question 7 for the main section of this paper before we move on to multiple choice. This question is all about radioactivity. So it's all about dice, which is a bit unusual for radioactivity, but it's a perfect model for radioactivity. We've got 900 dice, each with n sides to model the decay. A throw of the dice represents a constant time interval, and each dice represents a single nucleus. When the dice are thrown, those showing a 1 represent decayed nuclei and removed. Students count the number of undecayed dice that remain, and you sort of repeat. You might have done this practical, if not at A level, then probably at GCSE. And we've got a graph down here where if you look at the y-axis, we've got number of throws, but it's a logarithmic scale. It's not a linear scale. The first mark is just for saying, why would you do that? Why would we plot it on a logarithmic scale? So basically the answer is essentially because you've got like a wide range of results. So they cover sort of like many different orders of magnitude. So you could say the results or the data cover like multiple orders of magnitude. So otherwise you wouldn't be able to plot it accurately on a decent, like on a linear scale. But it just wouldn't work basically. You could also say that it's expected to be exponential, which they allow in the mark scheme here as well if you wanted to. So how we asked to use this graph is to work out the decay constant. So to model the radioactive decay, we asked to determine the decay constant and then asked to show that n equals 4. But let's work out the decay constant first. So the theory behind how we do this is to use our equation sheet. From our graph, we can work out the half-life. And we know that half-life t to the half is equal to ln 2 over the decay constant. So once we found the half-life, we just do ln 2 over it to find out our decay constant. So first things first is we do need to align a best fit. Don't ignore an easy mark like that. It's always worth doing. So do it properly, because with an order of magnitude, logarithmic scale, when you're covering different order of magnitude, even one small inaccuracy with your align best fit is not a good thing. You want as many points above it as there are below it. So I'm going to do something like that. And let's have a look at how many we start off on. So we start off on, if we look at the line here, each of these lines represents 100, so 200, 300, 400, 500. This is one line below 1,000, so it starts on 900. So we need to find 450. So to find 450, we are going to need to do, so this is 200, 300, 400, and we're going to do halfway between 400 and 500. So let's choose a different color to work that out. I've lost it now. 200, 300, 400, 500. So halfway between these two here, and then go down to find out how many throws, or essentially how long it's taken to do that. So this scale on the linear axis is normal. So this is going to be 3. I'd say that's landed about 2.5. So my half-life here is 2.5 throws. So then if we've got to flip over annoyingly, but that's 2.5. So decay constant is just ln2 over 2.5, which I'll write down our calculator quickly. 2.5 is going to be equal to 0.277, which is our final answer. However, it does give us another mark for working out what, showing, sorry, that n equals 4. So let's think about what this decay constant actually means. So decay constant in like regular activity is the probability of one nucleus decaying in 1 second. So effectively, how do we rate that here? It would be the probability of one dice landing with what side one up in one throw. So in terms of how the n equals 4, what is n? N was the number of sides. So if it was a normal dice, if it had 6 sides, you'd expect n to be 6, for example. We're not told how many sides it has, but for n is 6, we'd expect the decay constant to be 1/6. So therefore, to find n, we just do 1 over our decay constant, which is not 1/6 here, because we don't know how many sides we have to it. So it's 1 over 0.277, which hopefully if you round it correctly, we're going to get 3.61, which is equal to 4, which is what we're after in this question. Next up, we're talking about safety of different sources. So we've got typical radioactive source used in schools, has a reactivity of 100 kilobecquerels. In a hospital, 370 gigabecquerels. So that's roughly speaking, 10 to the power 6 difference between giga and kilo. So obviously higher activity says state one safety measure when using radioactive sources in a school lab, and then how would it need to be adapted to use it in a hospital. So basically get a mark for just saying a standard old school lab safety measure, then how do you make it different in a hospital? There are loads of different points for this. Don't overthink this question. I would say personally, I don't know, we'd say something like with sources, we say don't point at people. And then obviously with a much higher source, higher activity source, don't pointing is not going to be enough. We'd say don't allow others in the room when you're using the source, for example. That would be an example of what to do. So you could say store in the lead line box for the school source, but then you want to make sure you increase the thickness of the lead for the hospital source. You could say keep a big distance of like 2 meters in school, and then don't be in the room for when using the hospital source, and things like that. Next up, we've got information about X-rays are a form of ionizing radiation. It says a person has checkups to the dentist every 6 months. They only take X-rays when the person has reported a problem. Essentially, why don't we allow infinite X-rays to be used? So again, this is not a bad answer question to finalize the end of this section A of the paper. The idea is that ionizing radiation, which it does tell us in the question, so you don't get marked for saying that. So ionizing radiation damages cells, or you could say kills cells. You could say causes cancer or mutations, etc. If you wanted to, you don't need to say all these things, but just different things you could say. And the reason why you wouldn't have infinite ones of those is because, I don't know, you've got to talk about the risk of like what this will do if you have lots of X-rays versus the benefits. So something like you want to minimize the number of X-rays taken. I can't spell X-rays. There you go. Minimize the number of X-rays taken to minimize the risk. And generally, like a good comment is always to say something like, looking at do the benefits outweigh the risk? So making sure it's only done when it's a really, really important procedure. And that's the kind of thing looking for in this question. So let's move on to the dreaded multiple choice section. Some of them are tricky, some of them are easy. I'll try to point out ones that I think are particularly difficult as I go through. And if one's particularly easy, I'll try and rattle through them nice and quickly. So the first one says, which process is work done by an ideal gas? So 2 of these answers have things done at a constant volume. We should know that they're not correct if they're at constant volume. For work to be done is equal to force times distance. It's also equal to pressure times change in volume if you've done the engineering option. But both of those, there's got to be a change in distance. It's got to expand or contract So constant volume, that doesn't work. So we're left with these ones here. Is it doubling the volume at a constant pressure, or is it doubling the pressure at constant temperature? So it could be this one, because we know the volume's increasing because there's a change in distance of the size of the gas or the cylinder, whatever you're talking about. If you're doubling the pressure at a constant temperature, because temperature is constant, that means volume's constant as well. So it can't be D either. And the answer is C, doubling the volume at a constant temperature. Next one, we've got three molecules, which we get the speeds given to us, and we're after the RMS speeds, which is kind of unusual. It's quite a nice question, this one. So RMS, root mean square speeds. So to work out the root mean squared speed, we do exactly what it says there, but we do it in opposite. So we basically square them all first of all. So I'm just going to do the regular numbers. I'm not going to include the V. So 2 squared plus V squared plus 5 squared. And then we do the mean. So we find those, divide by 3, and we root them at the end. So if we do all those, we should get something around to 3.87, and we should stick V back on the end because that's where it was originally. Okay, question number 10, we get a bit trickier. We've got an ideal gas enclosed in an ideal insulated container with a small electric heater. The initial temperature is 300 Kelvin. The product of pressure and volume is 5,000 joules, which, as we said earlier, pressure and volume is equal to work done. So work done is pressure times volume. The gas expands at constant pressure, and it does 1,660 joules of work. So we're after the final temperature of the gas. So let's have a look at how these two things are related to each other. So essentially temperature and work. Okay, now because we know we're talking about temperature here, we only got information about volume and pressure and work done. So work done is proportional because it's at a constant pressure. Follow with me on this, all right? So work done is proportional to a change in volume. We also know change in volume, or any volume, is proportional to a change in temperature. So effectively we can say work done is proportional to a change in temperature. So therefore, if it's initially 5,000 and it goes to being goes up by 1,660, let's just do this in terms of ratios. So work done over 1 over 2 is proportional to work done equal to T1 over T2. If we know this is gone from 5,000 to 5,000 plus 1,660. And then this, we know we can figure out, well, if T1 is originally 300, what is T2 going to be? So if we put those in, this has basically gone up. That's essentially a ratio of 3/4, and therefore this has to be a ratio of 3/4. So the option is B, which is 400 Kelvin. Next, let's talk about a capacitor. It's got an air-filled parallel plate capacitor and resistor connected in series across the terminals of a battery. The plates are moved further apart, so D increases. So this change results in, like, what does it result in? So the idea is they're basically connected. So if they're connected with a capacitor, if it's connected to the battery, then V, the potential difference, cannot change. So V doesn't change if you have got it all connected across the battery. So therefore we know it can't be this one. That's the only thing we know it can't be first of all. So let's have a look at the equation for capacitance. We've got this one here, so A over D. So effectively that tells us that C is proportional to 1 over the distance between two plates, where D is that would be that distance there. So let's have a look at which of these two might be correct. So if we know that capacitance is going to go down when distance goes up, let's have a look, how does it relate to charge? Well, Q equals VC. Now if we said that V doesn't change, so therefore Q is proportional to C, if C goes down, then Q also goes down. So this one would be correct, or could be correct. Let's just check the other ones. Increase in energy stored, no, because both Q and C are going down and potential difference doesn't change. All the equations for energy have either those three factors in them, none of them are going up. And lastly, increase in capacitor, where we just said the opposite of that. So that wouldn't be correct either, so it's option B. On to question 12. This one's all about the efficiency of a transformer and which one of these will increase the efficiency of it. So with a transformer, I'm going to draw out the first one. So first one is increasing the thickness of the iron layers. So iron's in laminated layers, and thickness being bigger would mean you have less laminated layers. The reason we have those layers is to reduce eddy currents. So generally speaking, usually to increase the efficiency, you want to have a low eddy currents as possible. Those are currents throughout the material that are sort of a side effect of the magnetic field changing. We kind of want to reduce those as much as possible. Increasing the thickness of iron would actually increase the eddy current, so that wouldn't be a good thing. Decreasing the frequency of AC input voltage, I'm going to come back to that in a second. Decreasing the diameter of the copper wire. So if you decrease the diameter, you're actually going to increase the resistance, and that's not good because P equals I squared R. Heating will be higher, so that's not a good thing, so it's not C. Increasing the distance between primary and secondary coil. So these two here, the higher the distance, the lower the magnetic field or the change in flux, which you need. So that wouldn't be a good thing either. Now, the correct answer to this one is B, which I think is slightly insane, like how this is given as a question. It's not on your spec anywhere to know about the frequency. Having a little Google around online, there's a bit of sort of discrepancy in whether this is actually going to increase or decrease it. I just think it's a silly question to include for A-level paper. The general theory is if you decrease the frequency, that means you're increasing the time taken for the magnetic field to flip, basically. So the idea is if you're increasing that time taken, you are then, if you think about the EMF induced across the core, so Faraday's law, change in flux over change in time, if you increase that time, you are decreasing the EMF produced sort of in the core itself. In the coil itself, which I actually think that doesn't really improve it at all. So I don't really agree with this question at all. But technically it is B because you're reducing eddy currents, but yeah, not a big fan of that question at all, really. Next one, we've got a signal generator supplying a root mean square voltage of 7 volts. So RMS V is 7 volts. The voltage is displayed on an oscilloscope screen. It has 8 vertical divisions. What volts per division setting will display the tallest complete waveform? So big as possible, but you also need to be complete. So if RMS is 7 volts, we need to work out the peak voltage. So that's RMS over root 2. Sorry, let's say it right around, should we? So RMS equals peak voltage over root 2. So therefore, we do 7 volts times by root 2 to give us our peak voltage, which is going to be 9.89. Let's say 9.9 volts. So which of these would work then? So we've got 8 divisions, and we will find the complete waveform. So basically, we don't think the peak voltage is there to there. So peak voltage being 9.9, we need to figure out which one this is going to be. So we are going to need, if it's 8 divisions in total, we're going to need 1, 2, 3, 4 up there, 1, 2, 3, 4 down there to get to basically 9.9 or 10 volts. So if you have a look at all these different options, the best one to use is the 2.5 one, because we've got 2.5, 5, 7.5, and then 10, which just about fits our wave on, but fits a complete wave out as big as it can be. So it's option C for that question. Next question, we've got a kind of similar looking question here. We've got oscilloscope trace. Two waves are at the same frequency. You can tell because they both sort of pass the x-axis at the same sort of gap as they go down past the x-axis. We're told that the display has got a time base set to 5 milliseconds per division. We're after the frequency and the phase difference. Frequency is not too tricky. We've got F equals 1 over T. So the full time period, I would do it with this taller wave, so I think it's easier to do. So we've got one complete wave. Let's count the squares. It goes 1, 2, 3, 4, 5, 6 squares, 7, 8 squares pretty much on the nose to there. So each square is equal to 5 milliseconds. So 8 times by 5 times 10 to the power minus 3. And that gives us a frequency of 25 hertz. So we're left with C and D. Next is the phase difference. This one's a little bit trickier. So if you look at the phase difference, it's quite small. This one crosses the x-axis here. This one crosses basically 3/5 of a square after it, or 6/10, but it's the same when it comes back down. So I would do it in terms of, almost in terms of squares, because don't forget it is basically a ratio phase difference, is to say that if there are 8 squares in total, so there are 40, so 8 times 5 little subdivisions means 40 sort of small divisions. And then you can say it's basically 3 out of those, so it's 3/40 small divisions out. Now again, it doesn't really matter about like what the divisions mean essentially, but it's 3/40 apart from each other. So 3/40 is equal to hold on one sec, times by 2 pi to work out the phase difference, which gives us 320 pi, which is the same thing as 0.15 pi. So that's going to give us option D for this question. Okay, next up, we've got a cable which we're transmitting electrical energy across at a frequency of 50 hertz. And we'll ask which change gives the largest increase in efficiency. It's kind of similar to the transformers question from earlier, isn't it? Along the cable. So doubling the voltage let's have a think about what's actually going to cause the energy to be lost. So why doesn't the energy in equal the energy you have out? Almost always it's going to be due to heating, which is I squared R heating. So looking at factors that are going to affect those two things here, because that's what causes, or the equation that governs sort of to working out how much power is lost or how much energy per second is lost. If we double the transmission voltage of the cable, bear in mind we go P equals IV is another equation we can use. If we increase the increase the voltage, we are going to decrease the current. So that could be an option because we've got a lower current. Doubling the current, that definitely doesn't work. That's going to be more energy lost. Halving the resistivity, that's going to cause the same thing. So halving the resistivity of the wire itself, that's going to basically halve the sort of resistance because they're proportional to each other, increase the current, that's not a good thing. Halving the number of wires in the cable, similar thing, you're going to basically reduce the resistance and then you're going to increase the current. So for this one here, this is the only one that reduces the current, which is how we actually reduce the power lost due to heating. So it's going to be option A for this question. Next one up, we've got a question all about magnetic fields. An electron enters a uniform magnetic field at right angles. Flux density is B, moves at non-relativity speed. This is quite a standard type of question. You don't get given this equation in your equation sheet, but R equals mv over bq is a really useful one to be able to derive quickly. I'll show you where it comes from. It comes from equating the centripetal force mv squared over R to the force provided by a magnetic field. So getting rid of 1v and rearranging for R leads to this. Once we know that, and the number of circuits in 1 second, we're basically going to work out essentially the frequency. So frequency is equal to 1 over t. So we need to find an expression of a time period to get into this equation here. So what we're going to do is sub out v for v equals 2 pi r over the time period. So we could actually do f here, can we? But here I've started now. So r equals m and then 2 pi r over t. And then over b cubed, just subbing that in from put down there. So t goes to the bottom and we're left with m 2 pi r over b qt equals equals r. So if we rearrange this for t, so we're now left with t equals and then m 2 pi, that's a 2 over bq r over r. Obviously the r's cancel and we're left with m 2 pi m over bq. But we're after 1 over that. So f equals 1 over that whole expression. So we'll just basically flip it. So it's equal to essentially B. And instead of Q in this question, they want E because it's an electron. So E over, and then we've got 2 pi M. So therefore it's option D. So this question with lots and lots of detail in it is actually not too bad. If we've got a mass of this one here, we get given the masses in terms of U, the atomic mass unit of all three things. The energy released basically is going to be difference between this and this. So if we find that difference, then we're laughing basically. So I'm going to do the this one first. So the atomic, so the mass of our nitrogen nucleus, so 99925 minus, and this is all in terms of U, okay, so delta change in mass is going to be equal to that minus these two added together, so 13.0000. Just keep track of your decimal points, etc. with this question. That's the only way you can really go wrong, is if you're rushing. And that's all in terms of U, so that's going to give you a change of U of 0.0081. Now, because we're working out to mega electron volts, you could do that into kilograms and then do E equals mc squared and sort of work out in joules, then mega electron volts. But you don't have to. You get given in your equation sheet. Let's find it. So equation sheet says 1U is equivalent to 931.5 mega electron volts. So basically, to find our final answer here, we just need to multiply that by 931.5, which is going to give us 7.5 mega electron volts, option C. Next up, we're talking about binding energy. So this is a fission reaction, and we're after which statement is not true out of these. So the first one is that this element here, so this one has atomic number 57. It says has the greatest binding energy per nucleon of the 3 nuclides. So binding energy per nucleon of the 3 nuclides. You do need to be familiar with the graph of binding energy per nucleon and sort of atomic number or mass number down here. So if we have binding energy per nucleon, the rough shape of the graph looks like this. So we have the really light elements up here, then we get to iron, and then we go downwards. So iron, this peak occurs, iron 56. So we do need to be familiar with basically the rough nuclear number for iron, and that will help make sense of this question. So if we say that this one has the greatest binding energy, so uranium's down here, this element here is around about there. Let's go a mass number of 146, probably should be further to the end. The uranium was 235. Actually, this one, bromine, is going to have one that's much closer to the mass number of iron. So actually, this one can't be correct because this one is going to have a much higher binding energy per nucleus, just from looking at that graph. So therefore, this one is not true, and that's what the question's asking for. Let's have a look at the rest of the note and just figure out why they're not true. So why they are true, because the question was about not true. The mass of uranium is greater than the masses of these ones. Yeah, correct. You're going to have mass converted to energy, so therefore you're going to have a bigger mass to start off with. Binding energy of neutrons, yes, that is true, because neutrons are not attached to anything. Binding energy only applies to things that are attached to other nucleons. Binding energy of uranium is greater than this one. This one might catch people out. This is not binding energy per nucleon, it's just binding energy. And because there are way more nucleons, the binding energy of this one will be higher than this one down here, even though it's lower down on the graph, because this graph is binding energy per nucleon. Next up, question 19. We've got 5.6 kilowatt hours of heat energy released when a kilogram of wood pellets are burnt in a power station. What is the mass lost? So effectively, when we talk about mass loss, we are going to be talking about energy. We're going to talk about E equals mc squared. So we need to first of all find the energy and then use that to work out the sort of mass lost overall. So what we're going to do first of all is to work out the energy, so this into joules, because we need to put that into joules. So 5.6 kilowatt hours is obviously kilowatts we times by 1,000, so 5.6 times by 1,000, and then to get hours to seconds we are going to times by 3,600, or 60 squared. So if we do all that together, we get our total energy is equal to 2.02 times 10 to the power 7, and that's now in joules, which means we can use it. So after that, then what we're going to do is do m equals rearrange this equation. Basically, m equals E over c squared, which is equal to this divided by speed of light squared. So you can either, off the top of your head, it's 9 to the 10 to the power 16, or just do that. If we put that into our calculation, we should get 2.2 times 10 to the power minus 10. So that's going to be option C for this question. Next one, nuclear radius. So the relationship you're given in your equation sheet relates nuclear number to nuclear radius. So if I can find the thing, there we go. So this equation here, so nuclear radius R is equal to a constant times by a nuclear number to the power third. So that's our first thing to start off with. However, we need to use the terms here. So I'm going to use small a for this. So that's our general relationship. However, we've got to make a comparison. It says the nuclear radius of an element with nuclear number X is R. What's the radius of an element with nuclear number Y? So we are still using the same relationship, but we need to learn that if we've got it's got a different nuclear number, then basically instead of nuclear number in here, we just do proportional, the final divided by the original, but it's still to the power of the third basically overall. So we don't know if it's got bigger or smaller, but this relationship will still hold just for two different nucleons. So it's going to give us this one here, which let's just revisit a second, because that wasn't the most easy explanation. So if I could do y and x, let's just do the radius of y over the radius of x. Basically, that's probably an easy way of saying it. That's proportional to the ratio of the nuclear numbers. So therefore, our y, which is what the equation is asking for, is going to be equal to, so that should be equal to there. That's going to be equal to Rx, which they just said it's R here, so we can get rid of that. Is y over x to the power a third. So that's going to be same question, but a bit more detailed explanation because we've got the R in front of it, which is option D. Kepler's third law is a really important derivation. It comes up in this question, even though you don't have to derive the law, but we're after the radius of a synchronous orbit for a certain planet. We're told it has a radius r, we're told it has a mass twice that of the Earth, and a day is 1/4 of an Earth day. So that means that affects the time period. So we are going to use the same sort of start off. We're going to use the gravitational, using gravitational attraction, which is going to be equal to the centripetal force, omega squared r. We're using that because we can get t into it nice and easy. So let's do a little bit of rearranging. So if I get r comes from there down to here, and I get rid of one of the m's, we're left with omega squared equals gm over r cubed. So omega squared, we're going to substitute in for that. I was going to say 2 pi over t, so we can get a time period into this equation. So that's still going to be all squared, but it's now 2 pi over t squared. And let's just expand everything out. So we're now left with gm over r cubed equals 4 pi squared over t squared. So we need to find, basically make r the subject. Before we do that, let's get rid of some constants, because g's a constant, the mass of the planet's a constant, pi's a constant. Sorry, mass isn't constant, is it? G's a constant, pi's a constant, the mass does change, so we'll leave that one in there. So if I rearrange that, I'm left with r, and then r cubed is going to be equal to m over mt squared, and then to find r itself, I can do a big cube root of those two factors. Next is just about putting the values in. So we said the mass is twice the mass on the Earth, so we've got 2 times the mass, and the day is going to be a quarter. So it's going to be, sorry, I've made this really messy here, quarter, but it is a quarter squared, which is really important. So therefore we're left with times 2, but then also a quarter squared is going to be 1/16. So 2 times the 16th equals an eighth. So let's have a look at which one of these it's going to match up with. So because it's a cube root, this might catch people out, but it's basically a cube root of 2 times 16th, which is an eighth. So cube root of an eighth is 2. So 2 times 2 times 2 is 8. So actually this one is r over 2, which that caught me out, just the format of it a little bit. So let's have a look next at this next one. This question is about escape velocity. So escape velocity are not given in the equation sheet. It's a really useful one to be able to derive. We do kinetic energy of an object that's propelled upwards is going to be equal to its gravitational potential energy it gains. You're not given this one either, but you are given work done is equal to mass times by change in potential, which you're given both of those. You're given the potential equations, you can work it out from that. Let's cancel through one of the m's, and we're left with, if we rearrange for v, we've got 2gm over r, and obviously square root it right at the end. So if we're talking about the order of magnitude of the radius of an asteroid, we do have to rearrange that for r, which that's my bad, I should have realised that earlier, which is basically just switch out the v and the r, r's position. So if we're rearranging for this, we're going to have r equals, and then gm, 2gm over v squared. So let's then plug our values in. So this is 40. So it is sort of an order of magnitude estimate. I mean, I'll just work it out anyway because it just makes sense to. So 2 times by the g value, which is 10 to the minus 11, times by the mass, which is 2 times 10 to the 17, and then divided by 40 squared. If you put all those into a calculator to get r, we should get r is, I got 16675. You don't have to do it as exactly as that. However, there you go, 16,000. Yeah, that makes sense. 16,000. So that's about 10 to the power 4, roughly speaking. So 1,000 10 to the power 3, 16,000 10 to the power 4. That's the right order of magnitude for this question. Let's look at this question on equipotentials. So we've got some 2 objects where we've got their gravitational field lines shown to us and the equipotential for these 2 objects, which are both stars, and they have equal mass. We're shown these 2 things. We're asked which statement is correct. So let's go through them one at a time. There's more work done go from Q to S to R than go from Q to R. So let's go Q to S to R versus Q to R. No, those are going to be exactly the same. So when you move between 2 equipotentials in either direction, it's always going to be exactly the same work done, regardless of whether you go to there, or whether you go to here and here. So when you go to there, both those are no work done between them. So it's not going to be A. No work done going from Q to R. No, it does take work done to do that, so it's not going to be that one. Gravitational field strength is the same at R and S. Yeah, that's not going to be the case because the overall gravitational field strength at R, because R is closer to X, even though they're fairly similar distance from Y, because R is closer to X, it's going to experience gravitational field strength from there as well, and a different amount to S, so it won't be C. Process of elimination, that gives us D. I'll explain why this one is correct. So the work done going from Q to R and Q to S is the same. So Q to R is just change from one potential to another. Q to S, regardless of the sideways distance, it's no work done going from here to here. So if you go from there to S, it is going to be the same work done. Good fact to learn about equipotentials. How can we define the permittivity of free space? So which of these statements is equal to this thing here, permittivity of free space? First one should be obvious. It's not relative permittivity of a vacuum. We use epsilon r for that, so that's definitely not it. This is free space. We're talking about the next one. So the charge stored in a capacitor It's consisting of two parallel plates of area 1 meter squared, separated by 1 meter, when potential difference is 1v. Well, questions like this, there's loads of words in there, just highlight the numbers basically. So 1 meter squared, that's area. 1 volt, that's obviously PD, that's D. So that might give us a hint. We're going to have to use the equation C equals, and then we've got E0, ER, cross-sectional area divided by D. In this question, they talk about potential difference though, so we are going to have to sort of get that in there somewhere. So the general equation Q equals VC would apply. So C I can rewrite as Q over V. So therefore I can write, so Q over V equals C. So if I just rearrange that slightly, I can then do, but let's rearrange for E naught first. So E naught equals, and we're not going to worry about relative permittivity because we're just talking about E naught here. So E naught is going to be CD over A. So instead of C, I've now got Q over V, so I can put Q there and V down the bottom. And let's see if this all fits. So permittivity of free space is equal to Q, or the charge, sounds good. Two parallel plates, 1 meter squared, so that's area. So yes, we talked about that. Separated by 1 meter, yes, we talked about that. Potential difference, 1 volt, yes, we talked about that. So here's option B. I'm going to level with you. I don't really understand where these two come from. Don't understand pi meters, don't understand that at all. I'm not doing what AQ are doing with this one. The charge on a metal sphere experienced a force. I mean, there's no forces in any questions to do with capacitors. So yeah, wouldn't beat that one. But anyway, once you know this one is correct, then you can just stop there basically. This question on gravitational fields should be one of the quicker ones you can do on your A-level paper because it's just a simple ratios question. So with point charges, we've got Coulomb's law is equal to, so F is a constant times by charge 1, charge 2 over R squared. The magnitude of each charge is doubled and the distance between them is halved. The only thing that could catch you out is if you don't forget to double both charges. So we're doubling both because it says both magnitude of both charges doubled and the distance is halved. So because half is in our square root here, is in our square bracket here, we are going to have to make sure to square it overall. So we've got basically times 4 on top and we've got a quarter on the bottom. So that's going to mean if we look overall, we do a 4 over a quarter, which is going to be equal to 16 of what it was originally. So that's option A. This kind of question looks kind of insane. We're talking about a potential and field strength of charges. If we've got P at the center of all of these shapes, which one is going to be the resultant electric potential 0 and electric field strength 0 as well? Essentially what it's looking at is which one has the best lines of symmetry, best symmetry overall. This one has an overall charge of 0 overall. And if you were to consider, well, it's kind of even between left and right. However, between up and down, it's going to experience, let's say it was a negative charge, it's going to be repelled away from this one towards that one. So it can't have a resultant field strength. So this one looks okay because it looks fairly symmetric. You've got at each point, there's sort of equal amounts of sort of positive and negative charge. However, if you look at the overall charge, we've got plus 2q, minus q. That gives us an overall charge of plus 2q. So if we are talking about the potential, which is just like scalar, just looking at like not direction, overall there's going to be a positive charge on the particle. So therefore it can't be 0. Down here we have got V is going to be 0. So if you add up all the potentials, that's going to be 0. However, it's clearly asymmetric. Again, if it's a positive charge, it's going to be repelled away from here, or negative is going to be attracted towards there. So it's not going to be this one either. Let's have a look at D. If we add them all up together, we've got plus q, minus q, gives us 0 overall. And also it is perfectly symmetrical. So if you look at sort of the distribution of the charges, it is symmetrical. So it's going to experience an equal electric field from like the top half, bottom half, left half, right half, etc. So it is D for this question. Let's work out the direction of the electric field and the magnitude. But this time we've got a specific charge given to us, which makes things a bit harder because we do have to manipulate equations a little bit. So if you sort of imagine this, I'm not going to do the direction yet, but you've got the surface of the Earth, and then basically we've got a electric charge with an ion. We don't know if it's positive or negative yet. We do know it's negative, sorry, there we go. It's negative, but there's a field strength applied that basically we've got gravitational field going downwards, and there's going to be another field applied. So therefore you've got an electric field applied in a certain direction. We should also know that it's negative, it's going to be sort of held stationary, it's going to have to be pointing upwards. You've got this other field that's going to be acting the other way, that's going to sort of counteract the gravitational field and keep it stationary. So essentially you've got force due to gravity acting downwards on it, so mg. So let's consider the forces on the object. We've got force due to gravity equals the force due to the electric field. So mg is going to be equal to, and then force due to electric field is just electric field strength times by charge. And we don't know what that is yet, so we leave it like that. Now the reason we can get a specific charge involved here is because specific charge is equal to charge per unit mass. So if I rearrange this equation for charge per unit mass, I bring my m over here, so that we've got q over m on my right hand side, and then on the left hand side we're left with, bring my e over here, g over our electric field strength. So then we're trying to find our electric field strength, so we've got to keep this qm term together. So electric field strength is going to be g gravitational field strength over q over m. So obviously this is 9.81, this is 7.1 times 10 to the minus 7. So electric field strength, if you chuck down your calculator, gives you 1.37 times 10 to the minus 7 volts per meter. That's going to be one of these two then. I have to figure out, is it upwards or is it downwards? So because it's an electric, because it's a negative charge, is going to be attracted towards a positive plate. So that's the reason earlier I drew my positive part of the electric field. Obviously it doesn't have to be a plate, but whatever, up here. So positive plate, and I probably did misleading arrows earlier, is that when we have positive to negative, the field always goes from positive to negative. Even though that sounds counterintuitive, the field is directed downwards, but because it's a negative charge, it's going to experience a force upwards. So that's going to be option B for this question, because it goes downwards. Next one, if you were to work this out properly, it'll take you forever and you've not got anywhere near enough room on this paper. So I will show you how to work out properly, but I'm going to show you a little bit of a shortcut to work out the magnitude of the electrostatic divided by gravitational force for these different pairs of particles when separated by the same distance. So when we talk about electrostatic force, we are talking about, so overall we've got electrostatic force is EQ, or actually we should do, electrostatic force is so constant times like K1 Q1 over R squared. I'm going to leave out the R squared because it says they're at the same distance. Next one we've got is that's divided by FG, and that's a constant times by basically M1, M2. So essentially you're looking at the ratios of the charges versus the ratios of the product. So the ratio of the product of the charges over the ratio of the product over the product of the masses. So we're ignoring the distance between them, and I would just look through and see if you can find which one's got the highest charge and the lowest mass, basically. Now, little tip is that don't forget the mass of the electron is equal to roughly 1/2000th of the mass of a proton. So all of these have got protons in them. This is helium nucleus and protons. That means it's going to have a really high mass for all three, proton, proton, proton. This is the only one that doesn't have a proton in it. So that means you're going to have actually a relatively low mass product here. So even though the charges are all kind of similar, so this is, -1 plus 1, this is +2 plus 1, this is +1 plus 1, they're all kind of similar, whereas this is a big difference here is the masses. So I would just use that and like do process elimination, figure out the option is A. If you wanted to for each one, you could work out from the equation sheet. I mean, if you have time at the end of a physics exam, which said no one ever, you could find out the rest energy of the pions, for example, and then work out the masses from that. I just don't think that's worth your time. I think by figuring out that little trick there, there's a reason why there's no proton in here. So it's going to have the highest ratio because it's got the lowest mass by far of all these pairs because it hasn't got a proton in it. Next one, 29. I think this one, even though it seems easy, is a bit sneaky for AQA to put in because there's nothing in the spec about you having to know the specific value. But basically for gold scattering, you've got alpha particles go in and the nucleus of a gold is going to exert electric field strength on them, so much so that all their kinetic energy is going to go into electric potential energy at a certain point. So that R, sorry, that should be R there, is going to be the limit at which they stop, the velocity is 0 and they start accelerating back the other way. Now, that distance itself is just less than 10 to the power minus 14. It's called an upper limit on the nucleus or the size of the nucleus. But I think that's a bit mean to put that in there. You should be able to figure out it's either this one or this one. But yeah, it's 10 to the power 14 minus 14, the point at which that happens at. Okay, last two questions. We are almost there, people. We've got an NZ plot here. We're trying to figure out where this nuclei is supposed to decay by. So we've got its atomic number, 45, so that's here. And we have its nucleon number, which we can work out its number of protons. Don't forget this, number of neutrons. Don't forget this is the number of neutrons here. So what we do is we take the 45 and we go upwards. And the number of neutrons is just going to be 115 minus 45, which is equal to 70. So we go upwards till we get to about 70, and that's where it's going to be. As we can see, it's above the line of stability, which isn't labeled on here, but I guess it's non-radioactive, I guess. So we need to know if it's got too many neutrons, what's going to happen to it? Is it alpha, is it beta plus, beta minus, or electron capture? Got too many neutrons, the decay for a free neutron is it turns into a proton plus an electron, or a beta minus particle plus an antineutrino. So this means it's beta minus decay for all elements that have a bit too many neutrons. That's the most likely method it's going to decay, would be beta minus. In this next question, we're asked to figure out how many neutrons this uranium nucleus has after it's undergone these decays. So first of all, let's figure out how many it's got. Initially, it's going to have 238 minus 92, which is going to be 146 neutrons. So it gains one here. So let's just count them along, basically 147. Then at this point, we've got beta minus decay. Beta minus decay, as we talked about earlier, the decay is neutron changed into proton plus an electron plus antineutrino. So we lose a neutron here. So now we have 146 again. Then we have the same thing again. The nucleus decays again by beta minus decay. So 145. And that's this nucleus here. So how many neutrons does Z have? It's going to be 145. So to finish up with this paper, we've got a half-lives question. So let's look at what we've got. We've got an isotope lead-207. It was formed, it contained uranium-235, and it's basically decaying to lead-207 by a series of steps. We don't need to worry about all of it. So basically the biggest half-life is 0.71 billion years. It now contains one atom of lead for every 4 atoms of uranium-235. So basically that's really important. The ratio N over N0 is going to be basically 4. So one atom of lead for every 4 atoms, there's basically 4/5 of it. It's going to be uranium. So 4 versus there was 5 initially. So what we're going to do is basically use, as you might be able to guess, the exponential decay equation. So N over N naught equals e to the power minus decay constant over time. Decay constant we can work out because we know decay constant is ln2 over the half-life, and that's going to be ln2 over. We can leave it in billions of years because our answers are in billions of years. So let's just work this one out nice and quick. So ln2 divided by 0.71, which is going to be 0.976. So let's take logs of both sides to find t. So ln, we said this was 4 over 5, equals, and then we got minus 0.976 times t. So therefore t equals ln of 4 over 5 divided by minus 0.976. Which if you do all that, we should get 0.225. And again, this is billion years. I know I didn't change it because I don't need to, because it's in the question. So that's going to round to option A for this bit. And that brings us to the end of the paper. That is a really tricky paper. I was a slog just doing that and obviously pausing it myself to go through the questions. Really, really tricky paper. I know a lot of people found it really difficult. The grade boundaries for it were a little bit lower than usual years. And AQA actually released a new paper with some changes on it to make it apparently a bit easier for future years to use it as mocks and things like that. So yeah, really tricky paper this year. So don't panic if you've got a bit less than you normally do. Look at the grade boundaries. Hope you found the video useful. Please have a look at the playlist on the screen to find out more videos that you might find helpful for A-level physics. And I'll see you again next time.